Hello everyone, welcome to the first Systems and Control video, where we are going to solve an exercise involving state space representation. Consider a linear time invariant dynamic control system given by the following state space representation. So we have this, this one, and the output being y equals to x1 plus x2, where x of t is equal to this state, to these states. X1, X2, and X3. Okay, knowing or attending to these equations, x dot equal to a times x plus bu, and y equals to cx times du. They are the equations that represent the state space, basically. We can identify A, B, C, and D matrices. So, looking at this one, we can clearly see A matrix, here B matrix, and the C matrix given this output is given by 1, 1, 0, and not so relevant, D matrix equals to 0. Okay, we have the matrices A, B, C, and D defined. So let's add through the first topic, A. Okay, check whether the system is controllable, observable, stable, and stabilizable, and justify it. Is it controllable? Yes, it is controllable. That's because the system is in a controllable canonical form. Which where we have these A and B matrices standards form. So A is equal to 0, 1, 0, 0, 0, 1, and minus A3, minus A2, and minus A1. And B equal to 0, 0, 1. Okay, so because it is in a controllable canonical form, it is in fact controllable. Or we can opt by doing the controllability matrix given by this. But of course, it gives us lots of work and we don't want it. So we needed to prove also that the rank of M is equal to 3, and the determinant is different of 0. And this is a more direct approach, and that's why this system is controllable. Okay, now adding to the observability, is it observable? Okay, let's create the observability matrix given by this. And we know that C is equal to 1, 1, 0. Let's calculate CA. Okay, this is equal to 1, 1, 0 times the open loop matrix 0, 1, 0, 0, 0, 1, 3, 1, minus 3. Okay, so as we have a 1 by 3 matrix and a 3 by 3 matrix, we will have as an output a 1 by 3 matrix. Okay, so this is multiplying both matrices. We'll get that this will be equal to 0, 1 times 1 plus 1 times 0 plus 0 times 1, 1, and 1 times 0 plus 1 times 1 plus 0 times minus 3. It is equal to 1, in fact. Now, the last term, CA squared, we can simplify by just doing this. CA times A, and we know this from previous results. So let's use this row matrix 0, 1, 1, and once again multiply it by the matrix A 0, 1, 0, 0, 0, 1, and 3, 1, minus 3. Okay, once again, we'll have a 1 by 3 matrix with results 3, 1, and minus 2. Okay, we have our observability matrix given by this 0, 1, 1. No, sorry. It's 1, 1, 0, 0, 1, 1, and 3, 1, minus 2. Okay, let's check first if it is a full rank matrix. So it is equivalent to have 1, 1, 0, 0, 1, 1. And I'm going to take the last row and I'm going to subtract the last row to 3 times the first row. So we'll get that this will be equal to 0 because it's 3 minus 3. Okay. 1 minus 3 is equal to minus 2. And minus 2 minus 0, it's minus 2. Okay, now we can simply divide L3 by minus 2. You'll get 1, 1, 0, 0, 1, 1, and 0, 1, 1. Okay, we have two rows with the same elements. So if, once again, we subtract the last row to the second row, we'll get this result. 0, 0, 0. So, as we have a row full of zeros, the rank of this matrix is lesser than 3. So, what can we conclude? That the system is not observable. Okay, now going to the third one, stability. Is it stable? I'm going to make a more direct approach. So for this one, we need to get the open loop characteristic polynomial. And we can get that from matrix A. So we know that matrix A is given by this. And we'll get that the characteristic polynomial will be given by s to the cube plus 3s squared minus s minus 3. Why? Because it is a standard formula where this element is the symmetric of this one, of this element, the symmetric of this element, and the same for it to this one. So we have that the characteristic polynomial of A is s to the cube plus 3s squared minus s minus 3. Okay, this is the same as calculating the determinant of this. So it will give us the eigenvalues, of A. And to prove the stability, we want eigenvalues whose real part is negative. Okay, so how can we get the eigenvalues from this polynomial? We have to equalize it to 0. So we're going to equalize it to 0. And to save some time, I calculated in my paper, I calculated the solutions for this equation, and we got and I got that this is equal to s minus 1, s plus 1, and s plus 3 equal to 0. You may notice that s is the same of uh, the eigenvalue term. Okay, so it's just another notation. Okay, so we have that s equals to 1, s equal to minus 1, or s is equal to minus 3. So the system is not stable because we have at least one of the eigenvalues with the positive real part, which is this one. So it is not stable. Okay, now adding to the fourth topic, is it stabilizable? We can say that yes, it is stabilizable because it is controllable. It is controllable. But you have to pay attention that if the system is controllable, it implies that the system is stabilizable, but not vice versa. I mean, if a system is stabilizable, it is not necessarily controllable. And this is a notation that you have to keep in mind, okay? So the first exercise is solved. Let's move to the other one. Okay, let's move to the other one. And it is the following. Design a state feedback controller u equals to minus kx such that the closed loop system has a triple pole at minus 2. So we want to place a triple pole in minus 2, or in other terms, we want to do this s plus 2 to the cube. This is the triple pole at s equals to minus 2. And we want to implement a linear state feedback. Okay, there are two ways of doing it. So the first one, going by this method, by substituting u by minus kx, so we'll get that x dot is equal to ax times plus b times minus kx, and we'll get this this term a minus bk times x, and this is the closed loop polynomial. We could just make the determinant of a minus bk equal to s plus 2 to the cube. But this is a way that involves lots of work, and once again, we don't want it. So let's face the second approach, but just because we are into a controllable canonical form, So the value of k is given by this formula, alpha 3 minus a3, alpha 2 minus a2, and alpha 1 minus a1. So the alpha terms, they come from the desired polynomial or the desired triple pole. So s plus 2 to the cube can be simplified into this, and we'll get this polynomial, which I previously developed. So this is alpha 1, 12 is alpha 2, and 8 is alpha 3. Also, we know that minus a3 is equal to 3, minus a2 equal to 1, and minus a3, minus a1 is equal to minus 3. Okay, so now applying it directly, we know that alpha 3 is equal to 8, and it will sum to minus a3, so 8 plus 3, and then 12 plus 1, and finally 6 minus 3. And we will get that the K matrix will be equal to 11, 13, and 3. So with this, we have designed a linear state feedback controller.